Hello, Math 157ers. This is Professor D again. I'm going to talk about Section 9.2, and I'm going to break it down in a way that's going to make it easier and quicker to get through the material. So please bear with me. This will not be remotely as long as the 9.1 lecture. In Chapter 9, we are introduced really for the first time to this something called the student's t-distribution. Why is it called the student's t-distribution? Well, the man who invented this, whose name totally escapes me, worked for a company at the time where he couldn't put his name on this, so he just called himself a student, basically. So we're going to talk about determining t-values, and we're going to talk about constructing and interpreting a confidence interval for population mean. We use the t-value, we use the t-distribution to do our population mean when our population standard deviation is unknown. So I know I canceled the second group assignment, but if anybody had read it, you know, for the most part, we never really know when what the population standard deviation is. If we knew the population standard deviation, we would probably also know the population mean. So the t-distribution is a much more practical use for confidence intervals and hypothesis testing than the z. But kind of old school statisticians really want you to understand the z because it's based on principles that you already kind of know. So we're going to talk about the t here, but just to know that in a practical sense, the t-distribution for finding confidence intervals and then doing hypothesis testing is much more useful. So let's talk about the properties of the t-distribution, okay? A simple random sample of size n is taken from a population. If the population for which the sample is drawn follows a normal distribution, here's the equation for the t. Now this should look just like the z. Remember, let's see, this is going to let me write. Oops, I'm going to turn my pen back on. Z was x bar minus mu over sigma divided by the square root of n. What's different here in the t? Well, the population standard deviation isn't known. That's really a z, sorry. And that's the main difference between one of the main differences between the t and the z. Now, the t-distribution also uses this concept of degrees of freedom. Degrees of freedom is equal to n minus 1. So if you have a population size of 25, your degrees of freedom is 25 minus 1, or 24. And you'll see degrees of freedom usually abbreviated in DF. So if you had a population of, let's say, 29, then your degrees of freedom is equal to 28. Okay. Here they're doing an exercise in comparing the z and the t. So what they did is they took 1,000 simple random samples of size 5. It's sort of like that confidence interval example in the previous lecture. And they said, all right, so normal population with population mu equals 50 and sigma equals 10. They determined the sample mean and standard deviation for each of the samples. So they had 1,000 samples, 5 things in each sample, 5 numbers in each sample. They found the mean, no difference in how you find the sample mean, which is also the point estimate for the population mean. The big difference is for the z, we're going to use that for our sigma value, where in the t, okay, in the t, we're going to take those 5 data points and find the sample standard deviation. Okay, and remember in StatCrunch, the sample standard deviation is that one that's just called standard deviation. The population, the formula for population standard deviation, okay, was that unadjusted standard deviation and unadjusted variance. So here's what that histogram looks like. So there's that Z, doesn't look kind of like you can kind of draw and I'm an awesome drawer, so that looks really bad. But if I draw it nicely, you can kind of see it follows, gee, I still messed it up, but it follows sort of a nice distribution. Now the T looks a little bit different, okay? You've got some stuff going on over here. It's a little more spread out. It looks a little bit different, okay? So the big thing to tell here is that the histogram for that Z, it's symmetric, it's bell-shaped. That center of the distribution is 0, 0, and all those rectangles are going to fall between -3 and 3. Let's go back and see if that's true. Okay, and it's hard to see, but yes, it's -3 here and 3. Okay, so that's really, you know, it's kind of nice and close together. All right. So, but what's different with the T? The T has what they call longer tails. Okay, so look at these tails. See, we got to go all the way over here. Our tails go out to 10. Okay, so that spread in that distribution is really attributed to the fact that we used a sample standard deviation. So that number was different for every single sample of that 1,000. Whereas when we did the Z, we were using that one given to us, I think it was 10. Okay, so, you know, what changed? The only thing that really changed here each time was this X bar. Whereas when we did the T, this X bar and this S were changing. Okay. Now, here's some things about the T distribution. This first one, let's start that because that's very important. Its T distribution will be different for different degrees of freedom. And it used to be, we use this horrid chart to look it up, but I'm going to show you a way to do that in StatCrunch to make it much, much easier for you. Okay, again, area under the curve is equal to 1. Okay, and it's symmetric. So even though it spreads out longer than the tails, you know, at 0, half is below, half is above. Okay, and here, the last one, as T increases, okay, it never will equal 0, but as that T, as the T decreases, the graph will approach but never equal to 0, okay? All right, so the area in the tails is a little bit bigger for that T distribution, which we saw because the tails went out. Now, one interesting thing that goes on is if you have a very big sample, your T value will approach that Z value. Okay, so if your sample size gets to be very, very large, your T distribution really approaches that that Z. So in the dark blue line, the blue line has the normal distribution, and when the T is equal to, and it's hard to see because I did red and orange, so it's terrible. But the one with n equals 15 is that second one, that second line, and it's closer to the shape of the Z, than the one with n equals 5. I'm trying to draw that in for you. You can kind of see that there. How do we determine T values? Okay, so that T is alpha that we're going to be using confidence intervals. Is we find that area under the standard normal curve to the right. Okay, so we need to use a different calculator or a different table, but I'm going to show you how to use the calculator. Okay, so find the T value such that the area under the distribution to the right of T is 0.2. So, you know, your area, this area is 0.2. Okay. In the old days, we had to go to a table and look it up. And where is my StatCrunch? Oopsies. Let's go. Here we are. Now, you can go to Stat, Calculators, and look at this, T. All right, so come back to our PowerPoint slide, And let's remember what our degrees of freedom are 10. And we want to find the t-value, which corresponds to an area in the right tail of 0.2. 10. Now, what you do is this is what we did in the last lecture. We took that out. Area is going to be greater than or equal to, I know, I'm going to put something in here, otherwise you're not going to know what to do, 0.2. Compute shows me, okay, that's 0.2 for my t, and my t of alpha value is 0.879, probably 0.8791 or 0.8790, depending how the rounding goes. Don't worry about the rounding. Use what is calculated in here. All right, so let's see what happens. They did, 0.8791. All right, so let's look at, let's just do one or two more examples in here. Let's say the area to the right. Again, let's say what the area to the right is 0.2, but your degrees of freedom is 25. Let's get rid of this. Oops, 25, 0.2, 0.856. So it does change. All right. Now, what if my degrees of freedom were 1,000? 0.196. Oops, I gotta change this. Oops. It's gonna default to this. You want to make sure that carries to like 0.2. 0.8419. Now, I just want to show you, if I went back to my normal calculator, they don't let me have both up. This is the normal on the left. This is this one on the right. Mean is 0. I want to do x is greater than or equal to, I know, I got to put that in, 0.2, 0.8416, and look at this, 0.8419. What if this was 10,000? And I'm going to do that wrong. Look at this. When that law of large numbers comes into play. So when my sample size gets really big, this t of alpha value right here approaches the z value. And this is by the law of large numbers. All right, let's close that up so we don't get any more confused. Let's say you needed to find the t value for an 80% confidence interval. So let me just go to a new page. So let's say we had, let's find the t of alpha value for an 80% confidence interval. Okay, and let's say our n, I'm going to switch it up a little bit. Let's say our n is 31, which means our degrees of freedom equals 30. Now, what does an 80% confidence interval mean? It means that 80% is in here, 0.8, and each tail needs to be 1 minus 0.8, which is 0.2. Each tail is going to be 0.1. So, if we come back to here, all right, my degrees of freedom were 30. And if I put in 0.1, my t of alpha value is 1.310. Now there is a homework problem which says usually they're asking for those t values to the right, but as I was reviewing the homework problem before I started this, if it does ask for a t value, just a plain old t value, not for a confidence interval, because in the confidence intervals, you always use a positive t. Let's say degrees of freedom equals 19, and the area to the left is 0.056. I'm just making that up. Okay, area to the left is 0.056. So if I drew myself a little picture, it's this area over here that I'm coloring in is 0.056. So I would expect my t-value to be negative. So let's go back to StatCrunch. Degrees of freedom are 19. I'll take that out. 0.056. Less than. And there it is. Yep, it's a negative number, and that's okay. But when we're dealing with confidence intervals, we're always going to be using the positive number, the absolute value. All right, so let's go back to our lecture. Construct and interpret a confidence interval for a population mean. And this is just when I check to make sure like I'm still recording. All right, really simple. This looks just like we did before, except instead of z, got t of alpha over 2 and s. And that t of alpha over 2 is just like the, when I said for an 80% confidence interval and we did the area of the tail. Okay. Let's do an example. 95% confidence interval for the bacteria count. And let's see, pasteurized milk, random sample of 12 pasteurized glasses of work, and they actually gave us the data. Okay, here's the data. So we're going to need to find X bar. But first, we do a little check to make sure we can use this. So it looks like the distribution is approximately normal. All right, X bar, so they calculate this. X bar equals 6.41. And S equals 4.55. 95% confidence interval means that alpha equals 0.05, N equals 12, and our degrees of freedom are going to be 11. So let's, and I skipped right over StatCrunch. Here we go. Let's close this up. Go back to Stat, Key Statistic, Statistic, one sample, this summary. All right, now look, what's nice is that it talks about sample mean, sample standard deviation, sample size. So it is prompting you for the correct thing. So our sample mean was 6.41, and our sample standard deviation is 4.55. And our sample size was 12. We're going to do a confidence level of 95%. Hit compute. And 3.519 is our lower limit, and 9.3 is our upper limit. And they rounded to 2 decimal places. Okay. So let's just look at their example here. Suppose a student miscalculated the amount of bacteria and recorded a result of 2.3 times 10 to the 5. And we would include this value in the data set as 23. So what happens? Well, it changes our mean because we have an additional point. Our N is equal to 13 because we have an additional data point now. It changes our T, and it also changed our confidence interval. And that is really an outlier because it's outside of, look how much it changes your data and change the confidence interval. Okay, and that's an outlier. All right, so what I want to do quickly now is, let's go back here. I want to find a problem or two and just go over it with you. So I think I can go into study plan. Maybe the study plan is not up here. You know, if I go to chapter contents, Let's see if I go to chapter 9. All right, so let's find a good example to work on. All right, find the t-value such that the area in the right tail is 0.05 with 17 degrees of freedom. So they don't have StatCrunch up here for us, do they? So I do not want you guys to I want you guys to, here it is. Let's go back to number 2. Area in the right tail is 0.025 with 21 degrees of freedom. Go to StatCrunch, Stat, T statistic, oops, wrong one, calculators, T. And I already forgot the degrees of freedom. 21 degrees of freedom and 0.025. So we were going to put in 21. 0.025, is that right? And in the right tail is going to be greater than, so there it is right there. And I can Control-C that, copy it in 3 decimal places. That's 4, so I'm going to go with 80. 2.0780. Did not like my rounding. Let's try that again. That was 3 decimal places as needed. Right tail is 0.025 with 21 degrees of freedom. I know we did that right, so what is going on here? .0796, which should be 2.0. If you round that up, it should be 2.080. Hopefully now it'll tell me what I did wrong. Oh, I thought I put that in the first time. I don't know, 2.080 with the rounding. All right, let's practice. I want to show you 2 different types of confidence intervals. I know this is going to be small on your screen, but a simple random sample of size n is drawn. The sample mean is found to be 18.4, and the sample standard deviation is 4.1. Construct a 95% confidence interval for the mean if the sample size is 34. Stat T, 1 sample with summary. The sample mean is going to be 18.4. Sample standard deviation is 4.1, and the sample size is 34. And we want a 95% confidence interval. So you make sure you click where it says confidence interval, compute, and then we have our lower limit. And I'm real lazy, so I like to copy it in. Control-C, Control-V, 2 decimal places would be 0.97. And the upper limit, Control-C and Control-V that in. All right. I don't want to do that problem. I want to show you one where they give you the data. Come on. Here. All right. construct a 99% confidence interval for the mean concentration of dissolved organic compounds collected from organic soil. One thing I want to show you is they did actually give you X bar and a sample standard deviation, but if they didn't, you can click here and open your data in StatCrunch. Okay, so I have all my data, and I'm going to go stat T, one sample with data. So my data is in column 1, and we just have to click on confidence interval and put 0.99 and compute. Because it's going to do, this is cut off, it's going to do the calculation of your everything. It's going to take this and find X bar. It's going to find the degrees of freedom, which is 19 based on the sample size 20, and it's going to find the sample standard deviation, and it's going to do that all for you. All right, so that is all I have for this lecture. Hopefully that you found this helpful, and that's all I have. Thanks for watching. Bye-bye.